Beta Pictoris is one of the most photographed, most closely studied, most thoroughly documented planetary systems anywhere in the night sky. Astronomers have been examining it for decades, cataloging its enormous edge on debris disk, confirming two separate giant planets orbiting within it, and treating the entire system as a kind of open-air laboratory for understanding how planets actually form. And for all of that sustained, decades-long attention, there was a third planet sitting there the entire time, hidden in plain sight, completely undetected by every single observation ever made of this system, until the James Webb Space Telescope finally found it, not by seeing it directly, but by catching the unmistakable chemical scent of its own atmosphere. This is the real story of how NASA found a planet that had been hiding inside one of astronomy's most famous star systems for the entire history of modern telescopic observation, and why the specific method used to finally reveal it may end up changing how astronomers search for hidden worlds everywhere else in the galaxy. To understand why finding this particular planet felt so genuinely significant to the astronomers involved, you first need to understand just how well studied Beta Pictoris already was before this discovery ever happened. The star itself sits roughly 63 light years from Earth, young by stellar standards, at an estimated age of only around 20 million years compared to our own sun's 4.5 billion years, and surrounded by an enormous edge-on disk of gas and dust, debris left over from its own relatively recent formation. We got a system so bright and so close to Earth that it has served as one of astronomy's primary test cases for studying how planets actually assemble themselves out of the material surrounding a young star. This debris disk was actually one of the first ever directly imaged around any star beyond our own sun, first photographed back in 1984, and it has remained one of the most intensively studied structures of its kind in the decades since, precisely because its edge on orientation as seen from Earth gives astronomers an unusually clear direct view of its internal structure, layered rings, gaps, and warps that have provided crucial evidence for the presence of unseen planets long before any of those planets were actually confirmed directly. Astronomers had already confirmed two separate giant planets within this system, Beta Pictoris b, discovered back in 2008 and among the very first exoplanets ever directly imaged by any telescope, a discovery that itself helped establish direct imaging as a genuinely viable technique for exoplanet science in the first place, and Beta Pictoris c, confirmed several years later through a different detection method entirely, involving precise measurements of the star's own subtle gravitational wobble. By any reasonable standard, this was already considered one of the best mapped, most exhaustively examined planetary systems known to exist anywhere in the galaxy, studied continuously using nearly every major telescope and detection technique available to modern astronomy, ground-based observatories, earlier space telescopes, and now Webb itself, each contributing another layer of detail to an already remarkably complete picture. That is precisely what makes the discovery of a third planet, hiding within this same extensively studied system the entire time, so genuinely remarkable. In a paper published in the astrophysical journal Letters on July 15, 2026, a research team led by Aidan Gibbs, a postdoctoral researcher at the University of California, San Diego, announced the discovery of Beta Pictoris d, a giant planet carrying at least twice the mass of Jupiter, occupying the widest orbit of any of the three now confirmed planets in this system. Gibbs described the significance of the find directly, noting that this discovery adds another piece to an already fascinating planetary system, and that Beta Pictoris has long served as a laboratory for understanding how planetary systems form and evolve, with this newly identified planet now helping to tell an even more complete version of that same story. Here is the part of this discovery that genuinely sets it apart from almost every other exoplanet find in recent memory. Beta Pictoris b and c were both found using more conventional techniques, direct imaging, actually capturing a planet's own faint light in a photograph for planet b, and a combination of methods for planet c. Beta Pictoris d was found through neither of these approaches. Astronomers did not spot it as a bright point of light at all. Instead, using Webb's near-infrared spectrograph instrument, commonly referred to by its abbreviation NER specs, the research team detected the distinctive chemical fingerprint of an atmosphere, specific traces of carbon monoxide, water vapor, and methane, embedded within the light gathered from this specific region of the system, evidence of a genuine planetary atmosphere sitting there, even though the planet producing that chemical signal remained too faint or too obscured by the system's own bright, dense debris disk to be directly photographed in the conventional sense at all. Spectroscopy, the underlying technique behind this specific discovery, works by splitting light into its full range of individual component wavelengths, similar in basic principle to how a prism splits ordinary sunlight into a visible rainbow, except extended into infrared wavelengths invisible to the human eye. Every chemical element and molecule absorbs and emits light at its own unique, precisely documented set of wavelengths, meaning a detailed spectrum of light gathered from any particular point in space, effectively functions as a chemical fingerprint, revealing exactly which specific gases are present, based purely on which wavelengths of light show up as unexpectedly bright or unexpectedly dim within that spectrum. Gibbs and his colleagues specifically searched the spectrum gathered from this region of the Beta Pictoris system for exactly this kind of signature, and when they found clear, consistent evidence of carbon monoxide, water vapor, and methane all present together, in a pattern and concentration inconsistent with the star's own light or the surrounding disk material alone, that combination pointed directly toward a genuine, previously unknown planetary atmosphere, sitting in a specific, calculable location within the system, even without ever needing to isolate a clean, direct photograph of the planet producing it. This distinction matters enormously, and it is worth taking a moment to understand exactly why. Direct imaging, physically photographing a planet's own light, works best when a planet sits far enough from its host star, and bright enough in its own right, that a coronagraph can successfully block out the star's overwhelming glare while still leaving the planet itself clearly visible. Beta Pictoris' own famously bright, dense debris disk creates an additional, considerable complication on top of the star's own natural glare, scattering and reflecting light throughout the system in ways that can easily wash out or obscure a fainter planet's own signal, even with the most advanced coronagraph technology currently available. Beta Pictoris d, sitting in exactly this kind of visually cluttered, disk-saturated environment, may simply have been too difficult to isolate as a clean, direct point of light using any existing imaging technique, remaining invisible to conventional searches for years. Even as astronomers repeatedly photographed the very same region of sky, it was quietly occupying the entire time. Detecting its atmospheric chemistry instead sidesteps this specific problem entirely. Rather than needing to isolate a clean, but unambiguous point of reflected or emitted light against an already bright, complicated background, this method searches for the specific, telltale absorption and emission patterns produced when starlight or a planet's own thermal glow passes through or originates from a genuine planetary atmosphere, a chemical signature considerably harder for surrounding dust and glare to fully mask, even in an environment as visually cluttered as the space surrounding Beta Pictoris. NASA's own official announcement of the discovery specifically highlighted this technical distinction, noting that this represents the first directly confirmed planet discovered primarily through moderate resolution spectroscopy, rather than through traditional coronagraphic imaging, demonstrating that astronomers can successfully identify worlds hidden within visually complex environments by reading their atmospheric fingerprints, even in situations where actually photographing that same planet directly would remain extraordinarily difficult or altogether impossible. This is precisely why researchers are treating this discovery as significant, for reasons extending well beyond simply adding one additional planet to Beta Pictoris' already impressive roster. If atmospheric chemical detection can reliably reveal planets that remain effectively invisible to direct imaging, yet hidden within bright disks of dust and debris, or otherwise obscured by difficult observing conditions, it opens up an entirely new avenue for searching other, similarly dust-rich, visually complicated planetary systems throughout the galaxy. Systems where conventional imaging searches have likely already missed planets hiding in plain sight. In exactly the same way, Beta Pictoris d went undetected for years despite sitting within one of the most heavily observed star systems in the sky. Consider just how many other young, dust-enshrouded planetary systems astronomers have already spent years studying using direct imaging alone, cataloging visible disk structures, gaps, and warps as indirect evidence of unseen planets, without ever managing to actually confirm those planets directly, precisely because the same bright scattered light that makes these disks so scientifically interesting also makes any planet hiding within them extraordinarily difficult to photograph cleanly. Every one of those previously studied systems now represents a plausible candidate for exactly the kind of follow-up atmospheric spectroscopy that just revealed Beta Pictoris d, and researchers in the field have already begun discussing which specific systems might be the most promising places to apply this same newly validated technique next. NASA's own official statement on the discovery emphasized this exact point, framing Beta Pictoris d not simply as an interesting individual result, but as proof of concept for an entirely new observational strategy, one that could meaningfully expand the total population of confirmed exoplanets in visually complex systems that direct imaging alone has never been able to fully explore. It is worth being precise about exactly what researchers currently know and do not yet know about this newly confirmed planet, since that precision matters for understanding the genuine state of this discovery rather than overstating it. Gibbs and his colleagues have confirmed Beta Pictoris d's existence. Its approximate minimum mass of at least twice that of Jupiter, its status as occupying the widest orbit of the system's 3 confirmed planets, and the specific atmospheric molecules, carbon monoxide, water vapor, and methane, that revealed its presence in the first place. What remains under active investigation is a more complete, precise picture of its orbit, its exact temperature, and the finer details of its overall atmospheric composition, questions the research team has stated they intend to continue examining using additional Webb observations, refining this initial discovery into a considerably more complete scientific picture over the coming months and years. This kind of staged, incremental refinement is entirely typical of how genuine exoplanet science actually proceeds. An initial detection establishing a planet's basic existence and rough characteristics, followed by additional, more targeted observations, gradually filling in a fuller, more detailed picture over time, rather than a single observation ever managing to answer every possible question about a newly found world all at once. This discovery also arrives as part of a genuinely active, rapidly expanding body of exoplanet atmospheric research Webb has produced across just the past year, work that helps place Beta Pictoris D's significance in a broader, still unfolding context. In August of 2025, Webb detected strong evidence for a previously unconfirmed giant planet orbiting Alpha Centauri A, the nearest sun-like star to our own solar system, sitting just 4 light-years from Earth, a discovery that generated particular excitement given how close this specific star system sits to our own, making any planet confirmed they're an unusually accessible target for future, even more detailed study. In December of 2025, separate research revealed an unexpected atmosphere on TOI 5861b, an ultra-hot rocky planet completing a full orbit around its star in under 11 hours, a world so close to its host star that researchers had generally assumed any original atmosphere would have been stripped away entirely by intense stellar radiation, making the detection of any surviving atmospheric gases there a genuine surprise in its own right. That same month, additional observations captured dramatic streams of helium gas pouring directly off the puffy, low-density exoplanet WASP 107b, a so-called superpuff planet with an unusually low overall density for its size, actively losing material from its outer atmosphere in a visible, measurable stream. In March of 2026, a team led by researchers at the Carnegie Institution for Science uncovered compelling evidence for a genuine atmosphere surrounding TOI 561b's own extreme environment in even greater detail, describing it as a possible volatile-rich, wet lava world, complete with an active magma ocean continuously feeding and recycling the gases detected in its atmosphere, a genuinely exotic planetary environment unlike anything found within our own solar system. Michael Walter, director of the Carnegie Institution's Earth and Planets Laboratory, described this broader pattern of results directly, noting that these Webb-powered breakthroughs tap directly into Carnegie's own long-standing strength in understanding how exoplanet characteristics are shaped by planetary evolution and dynamics, and that considerably more exciting results remain on the horizon as this same research collaboration continues its work. And in May of 2026, Webb identified methane within the atmosphere of TOI 199b, a Saturn-sized planet notable specifically for maintaining temperatures surprisingly similar to conditions found here on Earth, a genuine rarity among giant exoplanets, which typically exist at far more extreme temperature ranges, either blisteringly hot, orbiting close to their star as so-called hot. Jupiters, or bitterly cold, orbiting at extreme distances the way Jupiter and Saturn do within our own solar system. Researchers studying TOI 199b specifically noted that its atmospheric chemistry could only be properly identified because specific elements and molecules absorb very particular, well-documented wavelengths of light, creating exactly the kind of chemical fingerprint that made both this discovery and Beta Pictoris D's own detection possible in the first place. Taken together, this steady accumulation of results reflects something genuinely important about where exoplanet science currently stands in the middle of 2026. Webb has moved well beyond simply confirming that other planets exist at all, a question effectively settled by earlier generations of telescopes and detection methods. It is now routinely characterizing the specific atmospheric chemistry of individual worlds scattered across a remarkably wide range of temperatures, sizes, and orbital configurations, and as Beta Pictoris D specifically demonstrates, it is capable of revealing entirely new planets that remained completely hidden from every previous observational method, simply by reading the unique chemical fingerprint their atmospheres leave behind, even when the planet producing that signature cannot be directly photographed at all. So here is the honest, complete picture behind what NASA and the James Webb Space Telescope actually found, hiding inside the Beta Pictoris system. A giant planet, at least twice the mass of Jupiter, occupying the widest orbit of any confirmed world in one of the most extensively studied planetary systems in the entire galaxy, went completely undetected through years of direct imaging attempts, concealed by the very same bright, dense debris disk that made the system such a compelling target for study in the first place. It took an entirely different approach, reading the chemical, fingerprint of its atmosphere rather than searching for its reflected light directly, to finally reveal that it had been there the whole time. And the same technique, now genuinely proven capable of finding planets no direct imaging search had ever managed to detect, may soon reveal similarly hidden worlds, scattered throughout other dusty, visually complicated planetary systems that astronomers have already been studying closely for years, without ever realizing exactly what else might still be hiding in plain sight. If you want to see what else Webb finds hiding in other well-studied star systems using the same chemical detection technique, subscribe and turn on notifications, because astronomers have already said Beta Pictoris still has more to reveal, and this newly proven method may be about to uncover considerably more than just one hidden planet.